Welcome to LabMinutes.com and our lab video series on MPLS. You can find a complete list of MPLS video on our website by clicking on the link above and sign up for our newsletters to receive the latest video updates. In this video, we're going to be looking at the way to provide a network redundancy with Fast Reroute, and this is going to be in the context of link protection. And along with that, we're going to touch on the concept of backup bandwidth as well as the bandwidth protection. Okay, so the idea of a link protection is that you have a link in your MPLS network that is very important, that you want to be able to route around that as soon as possible. And the way to do that, instead of waiting for the IGP to converge, which is usually take longer, what you're going to do is to pre-build a backup tunnels. So as soon as the router detects that the link has gone down, it can immediately redirect the packet that's supposed to go across that link into the backup tunnel. And that way, the experience with packet loss will be minimized. For our physical lab topology, we have 8 routers, R1 through R8, and one switch is switch 1. And here we have our router R2, 3, 4, and 5 connected in a full mesh topology across multiple serial point-to-point links, while the other routers are connected across layer 2 VLAN, as shown in this diagram. Okay, for our layer 3 topology in the middle, we have our core MPLS that's been enabled with MPLS traffic engineering. With the loopbacks 10 through 12 on router R6 and R7, that's not part of the MPLS, it will be used as our simulated test network. So the scenario that we have here is we have a tunnel that's going to extend from router 1 to router 2, and those going to be tunnel that's going to be carrying our traffic between R6 and R7. And then we're going to treat the link between R2 and R3 as a protected link. In that, we're going to build 2 backup tunnels. They're basically going to help routing the traffic around that link. And then we're going to see how the traffic gets rerouted into those tunnels when the link between R2 and R3 goes down. And the difference between those 2 backup tunnels are available bandwidth for backup traffic, and you will see that the traffic will be picking the backup tunnel over the other based on the bandwidth requirement of tunnel traffic. Okay, so we're going to start off with our configuration task number 1 by building a tunnel number 1 from R1 to R2 using the following parameters. And these are the bandwidth of 300 kbps, a path option 1 with explicit path of 3 and 2, so R1 will go directly to 3 and 2, and then we're going to use auto route announce for traffic forwarding. And then without dealing with a fast reroute or configuring link protection, we're going to shut down the link between R3 and R2 while trying to ping from R6 to R7 loopback 10, and then we're going to see how many packet loss that we might experience from that. Okay, so start with our configuration on R1, and again our network has been fully enabled to support traffic engineering, so we can go straight ahead and configure our traffic engineering tunnel. So for our tunnel 1, the IP unnumber loopback 0, and then tunnel destination, which is R2, so 0.2, which is R2 loopback 0. Now tunnel mode is going to be MPLS traffic engineering. Okay, and then tunnel MPLS traffic engineering, we're going to use auto route announce, and then bandwidth, this will be 300 kbps, and for our path option 1 explicit, we're going to name it R132, and now we have to specify what that explicit path would be. So explicit path name R132, next hop or next address will be 172.16.0.3, which is R3 loopback, and then 0.2, which is where the tunnel is terminated. Okay, so now our tunnel 1 came up, and you show MPLS traffic engineering tunnel. Our tunnels are up with a valid path, and it's currently going from R1 to R3 and then R2. Okay, so we already have a tunnel built, which is a red line right here. And now we're going to do a quick failover test. So we're going to ping from R6 loopback 10 to R7. Okay, so let me get ready to shut down the link. We need to shut down this link right here from R3 to R2. So let me get ready on R3. It will be serial 02:0. I think I missed a 0 right there. And then get ready to shut that down. And then let me hop over to R6, do a ping to R7 loopback 10. Sourcing from loopback 10, let's do just a repeat of 10,000, so we know that keeps going. And then we can do a size of 1300. Okay, so you can see those are pinging right now. Let's go ahead and shut. Give it a second. So right now the network has detected the link down and the IGP is trying to recalculate the alternate path. And it did that after 3 ping loss. So let me stop that. And we can just make a quick note. That's how much traffic we have lost during the network conversions. And now on R3, let's put that link back so we can move on to the next task and start building our backup tunnel. Okay, so that should complete our task number 1. Okay, now with our next task number 2 with link protection, we need to configure our 2 backup tunnels to protect the link between R2 and R3 using these parameters. In the first tunnel, we're going to give it a number 352. The first time we have a bandwidth of 500 kbps with only a available backup bandwidth of 3 kbps. So just because that the tunnel is reserved 500k worth of bandwidth, it doesn't mean that it needs to give them all up for the backup bandwidth. Here we just carved it out, the 300 kbps out of the 500 to make those available for backup traffic. And the path it takes is going to go from 3, 5, and 2. So it will be this brown line right here. So tunnel 352, and then our second tunnel is going to be 3542 with the bandwidth of 500 kbps. And all of those are going to be allocated for backup bandwidth. And this particular tunnel is going to take the path through R5, 4, and 2. So that would be our green tunnel right here. And once we have configured the tunnel, we need to configure R1 to utilize the backup tunnel and also increase the probability of it getting the bandwidth from the backup tunnel. As you can see that the bandwidth is limited to only those that's made available. And then we're going to run through another test to shut down the link just like we did earlier. Same thing with the ping from R6 to R7 loop back 10, and then we're going to make another note of the packet loss. Okay, so even before configuring the backup tunnel, what we can do is to get under tunnel 1 and let tunnel 1 know that it can use the Fast Reroute feature to reroute the traffic into the backup tunnel. With the command tunnel MPLS traffic engineering, right here we have an option for Fast Reroute. And if you question mark, there is an option right here called bandwidth protect. So what it does is just a flag that when R1 sends the path packets or RSVP path packets towards R2 along the path, it will let the routers in the path know that this particular tunnel will get a higher priority as far as getting backup bandwidth. And this is to fulfill the requirement to, that says, increase the probability of the tunnel getting the bandwidth from the backup tunnel. Okay, so that would be bandwidth protect, and as soon as you hit enter, what the R1 is going to try to do is to signal basically downstream from R1 through R3 to R2 and basically request for backup tunnel resources. Okay, so the next thing we need to do is to configure the backup tunnels on R3 to make that backup tunnel resource available. Okay, so now on R3, we'll first define our explicit path. This one's going to name R352, so it's going to be for the brown tunnel 352. Next address will be R5 and then R2. Okay, then we are going to configure another explicit path for the second backup tunnel, and we're going to call that 3542 with the next address of R5, then R4, then R2. Okay, for the tunnel 352, IP unnumber, loopback 0. Tunnel destination 192.16.0.2. Tunnel mode MPLS traffic engineering. Tunnel MPLS traffic engineering. Bandwidth. We said the 352 is going to have bandwidth of 500 with only the bandwidth available for backup traffic of right here. With that option, backup bandwidth 300. Okay, so we just allocate a portion of all the reservable bandwidth for the backup traffic. And then now we have to specify our path option. Number 1 is going to be type explicit and tie that to a path or explicit path name R352. Okay, so as you can see, the tunnel came up. Next, we're going to have to create another tunnel. So we're going to call this one our number 3542. And see, we can just copy for the most part from the other tunnel that we have configured already just to save us time, which is 352. All of these would be the same. Let's modify the backup bandwidth to 500 because that's what needs to be made available in the second backup tunnel. And then the other thing that's different is the explicit path name, which is instead of R352, we have R3542. Okay, so that tunnel is up. Before we define which links to be protected, in this case going to be this link right here, 0020 on R3. So we're going to tell R3 that for this particular link, you can utilize these two tunnels as a backup tunnel for that link. So that link's become protected. But before we do that, let me do a quick debug on RSVP. And we're just going to dump message so we can monitor all the RSVP messages that pass through R3. And then getting under serial interface, and to define the, you can see that we're getting some packets already. We'll take a look in a second here. Okay, so MPLS traffic, the command that you need is backup path, and we're going to tell the link to use the tunnel that we created for that. So let that kind of scroll through, and then it'll be 352, and the other one will be 3542. So as soon as you hit enter, you see some of the RSVP messages kind of flying by here. So let me kind of stop the debug. And then let's see what kind of messages we have, just to get an idea of what's going on in the background here. And this one is just a REST message outgoing from R3, probably going back to R1 because that's the direction the packet would be. Okay, and right here it still said the R3 has no local protection, so that's definitely before we enter the backup path command for the link. Okay, I just want to see if we can find the packets that's coming from right here, incoming path. So this is the path packets that's coming from R1 to R3, so that's why it's incoming from the R3 perspective. You can see the tunnel destination is going towards R2. Our hop address is coming from is 13.1, which is R1, and you can see all these explicit route that gets tied to the packet as well. And then what I want to show you is right here is the flags that's being set as part of the path packets. You can see that we have the local protection desire. So that means when we configured that fast reroute command on R1 basically flip on the bits for that flag and tells all the downstream routers that if there's any way to provide the link protection, then please do so. Then we also have the label recording, and this is for the RSVP REST packet to carry the label back to the upstream routers. And then we also have the bandwidth protection desires as part of the bandwidth protect option right here that we configured on the tunnel on R1. Okay, so that's coming from R1 to R3. And this is when R3 kind of passed on that same path message over to R2, okay, with the same flags and everything, bits set. And obviously the router R2 responds with RSV message. Same thing, this is incoming from R2. So you can see the whole process of the packets going back and forth. This is the outgoing back to R1. And this one right here, as soon as we enter that command with the backup path tunnel 352, the R3 generates an outgoing path message to R2 with the explicit route that goes through R5, which is our tunnel 352 right here, that goes through R5. And then here's the REST message coming back from R2 through R5 with the label attached to it. So it will be label 38. If you look at the show command on the tunnel 352, we should be seeing the label 38. And then you can see the outgoing REST message from R3 back to R1, but this time it tells R1 that the local protection is available on R3, and this is how R1 knows. And since we're dealing with link protection, the router R2 right here is considered a NHOP or next hop router. So you can see that there's a bandwidth to next hop, and there's some label information that goes along with that as well. So you can see how the routers is going back and forth and communicates to the upstream router whether or not a link protection is available. So now let's do some show commands. So on R3 to show MPLS tunnel 352. Okay, so obviously the path is up and it's going through 3, 5, and then 2. With this one out label is 37, and then we can look at 3542. That one is also up, and this one has an out label of 38. So those just showing the information on the tunnel in general. If you want to look at the information regarding the backup tunnel, then we can do a show MPLS traffic engineering fast reroute database. So it's telling you that the router R3 is currently providing a backup path or backup tunnel for the upstream source router R1. And also R3 in this scenario is considered a PLR router or point of local repair because that's where all the backup tunnels are originated. Okay, so define the input label and then the output interface under the normal operation, which is the link that's being protected. You can see that the label is using from R2 to get to R3 is an implicit null, and that needs to be the same label that's being pushed into the tunnel, because whatever that the R2 is expecting from R3, it will be expecting the same label coming from whether it's R4 or R5 backup tunnel. Okay, so here the fast reroute backup tunnel is tunnel 352. That's what's being used right now, and the status is ready. Okay, you can do the same command with the detail at the end. It gives you a little bit more information. So currently there are 2 backup tunnels. There is one protected interface, which is our 0020, and there's one protected tunnel, and that's the tunnel 1 coming from R1. And again, these are pretty much the same information that we already gone through, right? And there's several commands that you can do, and another one is show MPLS traffic engineering tunnel protection. And here we can see our 2 local tunnels, as well as the tunnel 1 that's traversing through the router 3. And again, it's telling you that for the fast reroute out label for tunnel 352 is going to be a explicit null. And then our final show command is going to be show IP RSVP. And here we have our fast reroute. Enter. So same thing, our tunnel that's being protected or it's going to perform a fast reroute on is tunnel 1 from router R1 on this protected link. And the bandwidth that needs to be protected is 300 kbps. It's currently using the backup tunnel of 352 with the label 0, which I believe that is a label number for explicit null. And state is ready and type is next hop. Since we're dealing with link protection, that's why it's marked as next hop. Okay, now let's see from R1 perspective, show MPLS traffic engineering tunnel protection. You can see that the fast reroute protection has been requested, and that is part of the flag that we saw on the debug messages. And currently we do not have the backup tunnel assigned, and here's some of the next hop or next hop information that it received back as part of the RESV message from the downstream routers. Okay, now let's go ahead and perform our failover test one more time. So before we do that, let's do a quick trace route from R6 to R7, sourcing from loopback 10. You can see currently it's taking 1327, which is the direct path right here, 1327. So now we're going to shut down this link one more time while we perform a ping. So on R3, let's have that ready, and then let's do our ping. Let me just do up arrow. This is what we did earlier. Let that run, and then we can shut that. Okay, so you can see that our ping paused a little bit, but nevertheless it keeps going right there. Not sure why we got additional packet loss there, but at the moment that we shut down the interface, we lost 1 packet. Although we kind of hope that we didn't see a packet loss at all, but that's still better than the 3 packet loss that we saw earlier. So now on R6, just to prove that the backup tunnel has kicked in, we can do another trace routes. And this time it's going through 13527. So now that link is gone, when the packet hits R3, since the tunnel 352 is pretty much being up and ready to go, all R3 needs to do is to redirect traffic into that tunnel, and it'll be able to get around the link that has failed to R2. Okay, so that's why we have currently is 13527. So 13527. All right, if you're now going back to R3, and let's check the status of the backup tunnel with the command show MPLS traffic. Let's see, traffic engineering tunnel protection. You can see it's that particular tunnel 352 is being marked as in use right now. Okay, and that is to back up the tunnel 1 on router R1. All right, so we can now see that our backup tunnel 352 is in operation. What we need to do next is to increase the tunnel 1 bandwidth to 400 kbps and see how this affects the backup tunnel being used. Okay, the whole idea is to kind of test our backup bandwidth configuration, since we said that the tunnel 352, although it has 500K reservable bandwidth, it can only use 300 of those for the backup traffic. Obviously, when we bumped up the bandwidth of tunnel 1 to 400K, it would no longer be able to utilize the tunnel 352. It would have to fall over to the next best thing, which is our tunnel 3542, although it will incur an extra hop, but that guy will have enough backup bandwidth to accommodate the new 400 kbps of the tunnel. Okay, so on router 1, let me shut that down just to clearly make configuration change. With the traffic engineering bandwidth 400, so bump that up, and then we no shut. Okay, I think we still have that link shut down, so let me kind of bring that up also. So no shut. Actually, let me kind of wait for this to come up first, and just to make sure we're in the right state, let's do shut and then no shut on that. Okay, and now if we go back to router 3 and let's do some show commands to show MPLS traffic engineering tunnel protection, you can see that the path is now being protected by tunnel 3542 because tunnel 352 no longer meets the bandwidth requirement. So that tells us that the configuration for the backup bandwidth command on the tunnel is working. Okay, same thing, we do show IP RSVP. Let's do fast reroute, enter. You can see that for tunnel 1 on R1, with the requested bandwidth of 400K, it now has the tunnel 3542 ready to kick in. Okay, everything else stays the same. State is ready, so that means we can give the failover test another try. Okay, and let me do the ping, let it run, shut. Okay, so you can see this time we don't even lose a ping, which is what we kind of expected the first time also, but this time we definitely did not lose a ping, and the tunnel, the link has gone down. And if you do the show command one more time with the tunnel protection show command, you can see that the tunnel 3542 is currently in use. And to prove that it's using green tunnel right here, we should see an extra hop that goes through R4. So let's do trace routes. And as expected, we have a packet that goes from 135427. Okay, so now we have 135. So once it hits router 3, packets gets placed into the backup tunnel, and then goes 5, 4, and 2, and then 7. Okay, and again, the way it works is as soon as the packet hits R3 and R3 knows that it needs to place the packet to the backup tunnel, all it needs to do is to prepend the MPLS packet, the out packet for that tunnel, and then the MPLS will pretty much take care of the rest of the routing. Okay, so R3 no longer have to wait for the IGP convergence to complete, and that's how we can pretty much minimize the packet loss when there's a failure like that happens. Okay, and that should complete our task number 2. Okay, so as you can see, the rerouting traffic using the Fast Reroute features is much faster than having the router to wait for the IGP routing table to converge, since we already have the backup tunnel pre-built, so the router can pretty much redirect traffic immediately just by selecting the appropriate outgoing MPLS label. So if you have a link that's very critical that the packet loss across that link needs to be minimized, then this link protection feature will be able to help you to achieve that. Okay, so that should wrap up our video on MPLS TE Fast Reroute with link protection. You can visit our website to view an extensive list of our lab videos and sign up to get access to additional lab contents. Thank you for watching LabMinutes.com, and I'll see you guys in the next video.